Hello, everyone. My name is Michael, and this is my research project. So, I did my research project on autonomous pathfinding using a Q learning agent. Um, the way my research project is structured is my research question is which exploration policy helps a Q learning agent find the shortest safe path while avoiding traps? So, the three that I chose was a fixed epsilon approach, where like it keeps epsilon the same or randomly changes it. It's a probability statistic. Decaying epsilon, which consistently decreases epsilon. And then UCB1, which targets actions with high uncertainty. So it uses this complex formula. And from my results, looking at our graph here, we can tell that clearly the green one, which was the UCB1, the green line had the quickest learning rate because the learning convergence, like the reward went up per episode much quicker than the blue or the red one, where like the red one is the fixed epsilon and hasn't even like reached its peak. We can tell by looking at UCB1 that it practically mastered the maze that I had given it. So you can see that using these heat maps, I'll actually show that in the demo, but can see that UCB1 clearly outdid all the other agents. Um, the UCB one also came up with this specific path, which I'm not really sure why it chose this one, and it repeated it multiple times, which is very interesting to me. Um, this was just a general example of what I assumed the path would look like, but it was very like wavy, which was very really interesting. Let's take a look at the actual code really quickly. So looking at the code. This is my Q learning agent. Essentially, there is two main functions aside from the constructor. Choose action is here in order to properly select epsilon in a way where it will not select epsilon. It selects the next best action. This part uses that UCB formula using UCB values. This one right here is if this is where the probability comes in. So if epsilon is in strategy, meaning if it's fixed epsilon or decaying epsilon, it's going to do a random dot random. And if that's less than the current epsilon, it's going to return a random int between them. Now, epsilon initially for fixed is zero point 0.1, meaning that in order for random dot random to really generate a number less than zero point 0.1, it's like a less than 10% chance. Meaning that for the most part, the fixed epsilon greedy will remain the same. The epsilon will 90% of the time remain the same, aside from a 10% of the time, where that 10% actually contributes to its learning in the sense that it kind of serves as a curveball to the agent. I also have a grid world class, which I'm not going to go too far into. It's mostly just getting the optimal path length and basically creating a grid of essentially like a grid where we lay out the maze. Essentially, right here is where we have the traps. So this is mostly where the barriers are and the bottlenecks, like right here, they're bottlenecks and walls that the agent is forced to learn. Um, the visualization.py is for the demos later, which I'll show you right now. This is the main code, training.py. So we'll import everything. Right here, I made a size, so the grid is going to be a 10 by 10 grid with 2,000 episodes. And then snapshot interval is not relevant right now, but here are the three strategies. Fixed epsilon greedy, decaying epsilon greedy, and UCB1. And then here's the environment. So I create a grid world object. And afterwards, we're going to define a research experiment function. So what this will do is it'll essentially train three different agents. So as you can see here, for strat and strategies, remember strategies are three different types. Going to make a Q learning agent. and then use that strategy right here in order to choose the next action. And from there, it will go through the grid, and the grid will return whether that the agent had run into a wall or whether it chose the proper path to take. Additionally, afterwards, if it is a decaying epsilon greedy strategy, it's going to multiply epsilon by 0.995, which is the decaying part. And it repeats this until it reaches 0.01. We can't have epsilon be less than 0 or 0, so 0.01 is the minimum that it could be. And then over here, this just keeps track of rewards and trained agents. Um, Now we'll run our experiment. So this is actually going to train several. Oh, I didn't run this cell. It's actually going to train the three different agents and store all of their values in these three functions. Now we'll go ahead and plot our graph. So this is similar to the graph we saw earlier. UCB1 clearly outdid both of um, the other fixed models, like the epsilon and greedy. Um, it's clear because decaying epsilon did better because epsilon was changing at a quicker rate. Fixed epsilon greedy was a lot more unstable. You could see decaying epsilon greedy eventually start to level out. Now, I also created some heat maps, which helps us to understand exactly what the thought process of our model is. Now, the way this heat map is structured is this is UCB1. Decided to show that this one more in depth in order for us to really see how UCB1 did compared to the other two strategies. UCB1 started off kind of similar to the other ones. Around episode 400 is where it makes like the path starts becoming more predominant. And from there, the more of the orange implies the more like that's the more like the confident or the confidence score of the machine. So this is the path that it took pretty much every single time. And then over here, oftentimes it could go down, it can go one more down. These were like the different types because it was more fluid over here. There's less walls compared to this little area. Now, if we looked at fixed epsilon greedy was much more chaotic. You could see that it didn't really have its own system going. It was exploring everything. It would take different routes multiple times. Same thing with decaying epsilon greedy. Could see more definition, but compared to UCB1, this is much less confident in its ability to solve the maze. Um, Now we're going to look at a live demo. So I made a function here, which allows us which trains the three agents. Well, this will train three agents and show us exactly what their thought process is. So let's take a look. So one thing I want to point out here is if you look at these episodes, you can see that it goes back and forth. This is because um, rather than going straight to the next line and getting a penalty, the machine is more confident in going back and forth between two cells because that's the way to maximize its profit. Otherwise, it might go into the red part and lose 50 points. Every time it goes to the correct box, it gains 100. If it stays in the same box, it loses 2 points. This is a kind of a motivational penalty. So that was fixed epsilon greedy. Decaying epsilon greedy had a similar start where it stops in one spot. I'm assuming it tried to go off the map initially. Um, Episode 600. So the first two, 300 and 600, only go up to step 15 due to like the lack of intellect within our machines at the moment. Around episode 900 is when it starts to really make its path down to the goal state. And then here is where it's perfectly mastered its like exact ability to do things. So if you notice, this is the same exact path that UCB1 took. Now UCB1, as soon as we hit episode 300, it's practically fully trained. If you see, it does all of this in one straight go. Like there's no need to repeat more than 300 or 600 like episodes. This goes up to 1200 just to show the concept. But really, within 300 episodes, UCB1 was able to fully complete the maze. So this uses the concept of reinforcement learning, where every time it does something, it gains a reward, whether it's plus 100 points or even a negative reward, which implies a penalty. So if it runs into the red, it loses 50 points. If it goes out of bounds, it loses 50 points. If it stays still, it loses 2 points, showing that it didn't make any decision, which still is the wrong decision. If you leave a question blank on a test, you're going to get a zero for that question. This is the same concept. So this is my research project. As I said, UCB1 was clearly much more efficient, especially because it takes in more parameters and does more calculations in order to determine the next state to go to. Thank you so much for listening and watching. I hope you learned something and yeah, have a great day.